Let's solve some exercises next. For each of the functions below, we have to describe its domain of definition, that is understood from the given formula. And the first one is this: f of z is 1 divided by 1 plus z square. So for this formula to make sense, the only thing we need to make sure is that 1 plus z square is not equal to 0. So that's why this is the solution. Since we need 1 plus z square to be non-zero, and the only two values of z for which 1 plus z square is 0 are I and minus I, so that means you have to remove these numbers. All the other complex numbers are allowed in the domain. So that is why this is the natural domain of this function. The set of all complex numbers z such that z is neither I nor minus I. Next part B, here the function is the principal argument of 1 divided by z. Now obviously here the only problematic point is 0. Every non-zero complex number has a unique reciprocal which is also a non-zero complex number, and which, because of that fact, has a unique principal argument. So we have written the solution like this. Since every non-zero complex number has a unique principal argument, the domain is the set of all non-zero complex numbers. That is, from the set of complex numbers we have removed 0. Part C, here the function is z divided by z plus its complex conjugate. In this case, we have to avoid those z values for which z plus z bar equals 0. Now z plus z bar is 0 if and only if half of that is 0. But you know that this quantity is nothing but the real part of z. So that means we have to avoid those complex numbers which have 0 real part. So the domain is the set of such complex numbers. That means purely imaginary complex numbers are not allowed. And finally we have D, where the function is 1 divided by 1 minus mod z squared. So again we need non-zero denominator, but let's see for that when the denominator becomes 0. The denominator is 0 if and only if mod z squared equals 1. If and only if mod z is equal to 1. Why do we not see plus or minus 1 here? That is because mod z is never minus 1. It can only be plus 1. And that is why the domain consists of those complex numbers which have absolute values not equal to 1. Geometrically speaking, this is the set of all complex numbers, that is the complex plane from which the unit circle centered at the origin has been removed. Next we have number 2. The previous one of course was number 1. I forgot to write the number 1. But anyway, so in this one we have to write this function in this form as u of x comma y plus I times v of x comma y. And the function is z cube plus z plus 1. Z of course is x plus iy. So with z equal to x plus iy, we just substitute z with x plus iy in this polynomial. So the cube of x plus iy plus x plus iy plus 1. And then we expand the cube using our usual binomial theorem, which works in the system of complex numbers just like it works in the system of real numbers. So you apply your usual formula: x cube plus 3 times x squared plus this second term iy plus 3 times x times iy squared plus iy cube plus x plus iy plus 1. Alright. Now x cube of course remains x cube, and this second term becomes, we have written I separately because we need to later gather the terms involving I together and those that do not involve I together. So I times 3x squared y. What happens here is you get I squared, so that gives you a minus sign. Minus 3x y squared. So here I does not survive. What is I cube? I cube is minus I. So minus I y cube plus x plus iy plus 1. So then we write the real and imaginary parts separately. For the real part, you collect those terms from this sum which do not involve I. X cube minus 3x y square plus x plus 1, and then plus I times the rest of the terms. 3x squared y minus y cube plus y. So this is your u of x comma y, and this one is v of x comma y, both of which are functions of two real variables x and y. In number 3, again a function is given, but this time already the function is given in that form, u of x comma y plus v of x comma y, where u is x squared minus y squared minus 2y and v is 2x minus 2xy, and where of course there is x plus iy. Now we have to express this function in terms of z and its complex conjugate using these two relations. X equals z plus z bar divided by 2 and y equals z minus z bar divided by 2i. Now one can of course take the long route to the solution by using these expressions and putting them here. Wherever x appears, you write this, and wherever y appears, you write this. Then simplify the expression, expand, do whatever you need to do. It will be a little big, but you will ultimately get what you want to get. There is an alternate method. If you can recognize the pattern, you can get the answer much more quickly. Let's see how we rearranged the terms here. We have kept x squared and minus y squared together. In place of minus y squared, I have written the square of iy. Y we will see, okay. And along with these two things, I have written I times minus 2xy like this. Minus 2 times x times iy. Why did I choose to write it like this? That is because I have an x squared here, and here I am having minus 2 times x times something. So there is a possibility of having a square here, and that too a square of something which we need. So the rest here is iy, and very nicely the square of iy is what you have here, because that's minus y square. Then what else do we have? We have minus 2y and I times 2x. I have kept them together. In place of minus 2y, I can write 2i times iy, because I squared is minus 1. And of course, I times 2x is the same as 2i times x. Now note that this part within the square brackets is the square of x minus iy. X minus iy is the complex conjugate of z, and x plus iy is of course just z. So now you have it. So it is equal to this, which is z bar square plus 2yz. So that's how you have expressed f of z entirely in terms of z bar and z. You do have an I here, but that's not a problem. You don't have x and y anymore. And finally, another one, number 4, where this function is given, z plus 1 divided by z, where of course z is non-zero. We have to express this function in this form, again as u plus I times v, but now u and v will be functions of the polar coordinates r and theta. So we start the calculation by considering the exponential form of z, which however exists because z is non-zero. For the zero complex number, there is no exponential form because argument is undefined. So then we of course just write r times exponent of I theta in place of z. Now this second term becomes this, because the reciprocal of e to the power I theta is e to the power minus I theta. We have already seen these things before in the previous chapter. And then we write what these exponents are. That one is cos theta plus I sin theta, and this one is cos theta minus I sin theta. And then you collect the real part and imaginary part. The real part will be r plus 1 divided by r times cos theta, and the imaginary part involving I would be I times r. Don't forget that there is an r multiplied with this r times sin theta, but sin theta is also a common term, so you just have r minus 1 divided by r times sin theta. So your u r comma theta is this and v r comma theta is this, not including that I.